hopefully you know how to share your screen, but I'll introduce you first.
Okay.
Yeah. Okay, so delighted today to introduce Jay Cullen. He's currently you're currently a professor and provost engaged scholar in Earth and Ocean Sciences at the University of Victoria. But just looking through your CV, see where you've been, did your BSc in McGill in Montreal, and then a PhD at Rutgers with Rob Sherrill, and then a postdoc at Woods Hole. And then Jay has been at the University of Victoria since 2003. So Jay is a close colleague of Christian and I, and we know him mainly for some of his early groundbreaking work, looking at sort of trace metal cycling, uptake quotas into phytoplankton, things like what controls the global distribution of cadmium and phosphate, some of these trace metal nutrient relationships. And so this is work Jay still does. He's most recently been looking at things like how trace metals are removed in oxygen minimum zones, and this is some work we did collaboratively with him and his student Dave Jansen. He's also been doing a lot of work on trace metal cycling in the North Pacific, where he's been very involved with the Line P program, with the Canadian Coast Guard, looking at this sort of repeatedly cycled time series. Also, Jay has been very involved in Arctic geotraces recently. I think very involved, maybe leading the Canadian effort, which has been combined with the US and German efforts to look at the Arctic Ocean for trace metals and carbon cycling recently. And also, most recently, I think he's been very involved in looking at the impact of release of radiation from the Fukushima disaster in 2011, especially sort of monitoring and looking at the impact of, or how much of the radiation arrives in British Columbia, and leading the INFORM project. And so he has lots of interesting stories about how he's interacted with the public on social media in various different forms that I'm sure he'll tell us about. But over to you, Jay.
Well, thanks for that introduction, Tim. I really appreciate it. It's true. I will speak about those experiences today and share a little bit about what I think I've learned from it. I wish I was there in person. I'm just going to start my presentation. Is that coming through there that you can see?
Yeah, we can see.
Yep.
Yep.
Okay, that's great. As I was saying, I wish I could be there in person. I do know some of you quite well, and I had a great meeting with the graduate students this morning. I'd like to experience some of the heat that you've got there. It's quite cool, quite windy today in Victoria, although I know better than to complain to a bunch of Floridians about wind during hurricane season, so I won't. What I will talk to you today about specifically is this project that's been running over the last 6 years. And I've got lots of collaborators who have contributed and moved this work along related to understanding what the environmental impacts are of the radionuclide contamination released from the Fukushima Daiichi nuclear power plant back in 2011, 9 years ago now. Time seems to be flying. And so this work was sponsored by MEOPAR, which is one of the networks of centers of excellence here in Canada. As well as NSERC, our national science funding body here in Canada. I just wanted to acknowledge that. So what we'll do today, briefly, is to put the releases from the triple meltdown at the Fukushima Daiichi nuclear power plant into perspective with respect to radioactive elements that are always present in the environment and have been with us since the planet formed. As well as human caused or human manufactured elements that wouldn't otherwise exist on the planet. And then I'll talk to you about the INFORM project, so how it came about, what its structure was and its goals were, and the progress that we've made thus far as the project is sunsetting. And then talk a little bit about the response to knowledge mobilization and outreach, some of the science communication work that I've been doing, and again, what I think I may have learned from that, although it's not abundantly clear to me what that might be. So just as a broad introduction, when we talk about radioactivity, what's great about radioactive elements is that they're releasing mass or energy that we can detect, and we can detect that very well at very low levels. So for an analytical chemist like me who's used to counting ions, detecting radioactive decay seems like magic. It's really quite impressive, the number of atoms that one's able to detect in the environment, given their radioactivity. We measure that radioactivity in a unit called becquerels, which is simply a decay of an element per second. And when we talk about human exposure and the potential health implications of being exposed to ionizing radiation, we use a unit called the sievert, and that takes into account the type of radiation that's being emitted, whether that radiation is being emitted externally or internally to the organism or the human being. But for the most part, we'll be talking about the number of becquerels that we detect, for example, in a liter or a cubic meter of seawater, or perhaps in a kilogram of tissue from a living organism, mostly today. Now, just so we understand how much radioactivity exists in seawater, if I were to go into the open ocean and return with a liter of seawater, there'd be about 14 becquerel per liter there. Or if you think about a cubic meter, 14,000 becquerel, 14,000 decay events per second in that volume. Now, most of those decays are occurring because of naturally occurring long-lived radioisotopes that have been present in the environment forever. About 7% of those decay events occur because of elements that, because we've been able to sort out how to fission elements, we've got fission fragments and heavier elements from neutron capture that exist in the environment that we've produced that contribute to that total amount of environmental radioactivity. But most of it that's there in seawater is there because of naturally occurring elements and isotopes. The isotopes I'll tend to focus on today, I'll do so mostly because the amount of that element that was released during the meltdowns at the nuclear power plant site tended to be large, or because they're sufficiently long-lived that their potential to contribute to health risks to human beings or to marine organisms are greatest. And that really relates to their chemical similarity to elements that we need for our physiology. Iodine 131 has a very short half-life, so the risk from that release was front-loaded to the weeks and month after the disaster itself. But because it's iodine, our bodies can concentrate it, and it can cause problems when it decays. The cesium isotopes 134 and 137, with a 2-year half-life and 30-year half-life respectively, are chemically identical, mostly, to potassium, which we need for nerve function and otherwise inside cells. And so organisms concentrate that cesium into tissues that can be damaged. Similarly, strontium-90 is like calcium. It gets taken up into teeth and bones. And when they decay there, they can cause damage to DNA, for example, that can lead to certain types of cancers, and that's the risk. So these elements and isotopes were released in relatively large amounts during the disaster, and they persist in the environment mostly long enough that they can cause problems by getting into marine food webs and ultimately up to human consumers. Now, we also measure the cesium isotopes, for example, because 134, with its 2-year half-life, it means that most other either catastrophic releases or bomb production of this isotope are sufficiently distant in the past that it's all decayed away in the environment, so that early on in the disaster after Fukushima, if we detected 134 in a sample, we knew that that was Fukushima impact. So it was a real important fingerprint or tracer of the Fukushima disaster early on. And because we can measure cesium along with potassium, for example, using gamma spectrometry, it's information rich. It gives us a lot of information for kind of a simple analysis. So the cost of these analysis factored in, we get good information to cost ratio there. Now, the graph that you're looking at now is just compiled from reports on the total amount of radioactivity of radionuclides that have been released to the environment above the dashed line here on the figure to the atmosphere, and below the dashed line, ultimately ending up in the ocean, from different human activities. So on the left-hand side, we've got nuclear weapons testing, which was occurring in the middle of the last century. We've got fuel reprocessing facilities where spent nuclear fuel rods are reprocessed, leading to releases to the environment. The Chernobyl disaster in 1986, which led to significant releases in the Northern Hemisphere, and then the Fukushima disaster in 2011. And what I want you to take away from these very schematic figures The size of the circle really corresponds to the amount of radionuclide released, and we're looking at 90 strontium and 137 cesium, and these are in petabecquerels, which is 10 to the 15 becquerels, so enormous amounts of radioactivity. You can see that weapons testing, it turns out detonating nuclear weapons in the atmosphere is a bad idea if one's concerned about global contamination with these radioactive elements. Very large amounts, 600 petabecquerels, 950 of strontium and cesium respectively to the atmosphere. And because most of our surface is ocean, the majority of that ended up in the world's ocean. Most of that testing is done in the northern hemisphere, so I'll show you that because of the mixing ratios in the atmosphere, most of it is ending up in the northern hemisphere oceans. We've got fuel reprocessing facilities in Northern Europe, in the UK and in France, direct releases of cesium-137 and strontium to mostly the North Sea, as we'll see. And in Chernobyl, that explosion and burning of the reactor core in the open atmosphere for about a week to 10 days led to significant releases of cesium-137, smaller amounts of strontium to the atmosphere, with some fraction of that ending up in northern hemisphere oceans. And in comparison, you can see, based on measurements of air, of soil, and of water, releases from Fukushima were about an order of magnitude lower than for the Chernobyl disaster, and very small amounts of strontium-90. But that most of the radioactive elements released from the power plants in Japan ended up ultimately in the ocean, and in the North Pacific specifically, such that much more than any other human activity, any other disaster, the Fukushima disaster is primarily a marine disaster, and that's one of the reasons why oceanographers are focused on it and what the potential impact that might have on ocean health and public health. But by far, until the weapons treaty ban in 1963, atmospheric weapons testing dramatically contaminated our environment with these artificial radionuclides. Now, how did these releases in Japan occur? Well, about 10 years ago now, there was an enormous earthquake, one of the largest that we've measured with modern methods, magnitude 9, that occurred just offshore, about 70 kilometers, this megathrust earthquake just off the coast of Japan. And it moved the main island of Honshu almost 2.5 meters towards North America. I always joke that means that it's easier to fly to Japan now. But there's nothing really to joke about with respect to the impact of both the earthquake, the subsequent tsunami, as we'll see, and ultimately the nuclear meltdown. So a triple disaster that the Japanese people are still recovering from along the coast. The tsunami that was generated by the vertical motion of the ocean plates led to a tsunami that was 40 meters, 130 feet high in sort of more restricted coastal areas. And in low-lying areas, that wave traveled up to 10 kilometers inland and absolutely destroyed many coastal villages and cities, both in terms of infrastructure and in terms of lives lost, a terrible disaster. And it's something that we think about here on the West Coast because we're due for an earthquake of this magnitude. And it's pretty clear we're unprepared for it. So it's my duty to remind those who have family members along the West Coast that this one is coming. Now, when that tsunami arrived at the Fukushima Daiichi nuclear power plant, which is on the west coast of the main island of Honshu, when the shaking started in the plant, the reactors shut down as designed. And there was power loss because the reactors aren't running and because the earthquake damaged power lines coming to the plant. There are emergency generators that circulate water around the fuel rods to keep them cool, because even though they're not actively fissioning, there's a lot of decay heat and heat that can damage the fuel rods and lead to radioactive releases. And those generators were humming away and doing their job and keeping the cores cool in reactors 1, 2, and 3 at the site. However, when the tsunami arrived, those reactors were below grade and they were flooded and they were destroyed. And so without cooling, there was catastrophic damage to the fuel. The fuel melted and melted out of reactor containment and led to radioactive releases to the atmosphere. but also emergency efforts by the Japanese at the site, the workers to keep the fuel cool by pumping seawater directly into the reactor pressure vessel led to the contamination of that water, which ultimately was running off into the coastal ocean. So we had atmospheric releases, direct discharge of radionuclides to the coastal ocean, and then atmospheric releases that were to the Japanese mainland were ultimately mobilized by rain and river water and groundwater flow that brought it to the ocean as well. So this is a figure that Ken Bissler put together. I'll mention Ken again as we move on and talk about the results of the project. But the releases from the site peaked. There was a dramatic pulse into the coastal ocean and the atmosphere in the days and weeks following the disaster. But those releases continue today, but are much smaller in magnitude than they were in the early days of the disaster. This is another figure from Ken that shows the concentration activity of cesium-137 in the world ocean before the disaster at Fukushima, to give some perspective. And so what you can see is that because of atmospheric weapons testing in the Northern Hemisphere, we had activities on the order of 3 becquerels per cubic meter of seawater. In the North Sea, we see some impact of fuel reprocessing in the Irish Sea. So Sellafield and La Hague direct releases to the ocean, 61 becquerels per cubic meter of cesium-137. We see the impact of Chernobyl in the Baltic and the Black Sea, so 40 and 16. And what you see as you move into the Southern Hemisphere, because weapons testing was occurring primarily in the Northern Hemisphere, we have sort of less than a becquerel activity of 137 per cubic meter of seawater. And in the North Pacific off of BC and off of Japan, we had about 2 becquerels per cubic meter in 2008, before the meltdowns occurred at the Fukushima Daiichi site. So just keep those numbers in mind. About 2 becquerels per cubic meter in the North Pacific. Now, this is a figure from a paper by Pavel Pavanich and Hirose in 2015. And if you look at the y-axis, it's logarithmic for 1. And these are in units of becquerels per liter. So we have to multiply these by 1,000 to get to becquerels per cubic meter. And you can see in the coastal seawater at this Fukushima Daiichi power plant site, we've got on the order of 100 million becquerels per cubic meter of cesium-137 close to the coast. Very high levels of contamination in the days and weeks following the meltdowns. But that very rapidly, the release rate diminished and the activity concentration is being mixed out and transported away from coastal Japan. So that even a couple of years later, and if we extend this out in time to now, levels are similar to what they were before the disaster, but still higher than we would predict, showing that there's still contaminated water making its way from the coast of Japan into coastal seawater. But very high levels that dropped off quickly with continuing contamination of seawater at the site to this day. Now, I was interested in this when the meltdowns were occurring, when we were getting reports that the power plant itself was in trouble for a number of different reasons. But the main reason was that I knew that my family and my friends were downwind and down current from these releases. And what you're looking at is a movie of modeled transport of radioactive cesium-137, as well as measurements that have been made over time. And you can see that the North Pacific Current, the oceanographers in the crowd will know this quite well. The North Pacific Current is bringing that contamination across towards North America, and it bifurcates into the Alaskan Current and the California Current, more or less at the latitude of Vancouver Island, where I'm sitting just here. So we knew it was coming towards us, and the question became, how much contamination would there be, and what would the potential impact be, not only on the health of the North Pacific Ocean, but on our fisheries here in Canada, and ultimately on public health here in Canada as well. So that was the motivation. The other motivation is that immediately after the disaster, it became clear that there was a problem with getting quality, scientifically sound information to the public. In Canada at the time, we had a government that was really preventing federal scientists who were doing a world-class job of monitoring the atmospheric contamination and the marine contamination from speaking to the public. And into that vacuum, tremendous amounts of misinformation and terrible pseudoscientific information was rushing in to fill the void. And you could read headlines that the North Pacific Ocean had been sterilized, that it was dead, all sorts of scientifically unsound conjecture and just things that were being made up. And so I felt as a scientist it was part of my duty to the public to provide them with information that was sound so that they could make decisions about protecting their health and safety and their families and friends. So that motivated me to get a group of scientists together to write a proposal for the integrated Fukushima Ocean Radionuclide Monitoring, or INFORM network. And this was a collaborative effort between academics, federal scientists working in the federal laboratories, non-governmental organizations, and citizen science volunteers to conduct this health assessment of what this disaster meant for the North Pacific and for the Arctic Ocean here in Canada. And we were funded in 2014 for a period of 6 years. So here are the partners. I mentioned them before. Lots of people doing fantastic work early on in the disaster to monitor what was going on. Ken Bissler at Woods Hole, our Health Canada scientists with the Radiation Protection Bureau, Jing Chen, and Jack Cornett at the University of Ottawa, and our federal scientists, John Smith, Mark Trudell, working for the Department of Fisheries and Oceans. So we've got academic institutions, international partners, our government laboratories, and then our NGO partners. And I'll come back to them in the future. At the beginning, I thought, won't it be great, or won't these organizations be excited to be involved in this great science project? In the end, it was the tail wagging the dog. These organizations really helped bring about the success of this program, and I can't stress that enough. I'll come back to that. So what were our goals? Well, we wanted to deliver quality information to the public so that we could conduct a radiological impact assessment of the disaster for Canadians. We want to get this information as quickly as we could to people so that they can make decisions about their health and their family's health. So before peer review, we wanted to be generating quality information and getting it to the public quickly. And we wanted to leave a model where we would have a network of scientists and citizens and organizations that were concerned about marine health so that we could rapidly respond to other types of marine disasters. So a great example, both in the Gulf and here on the West Coast, is the potential for an oil spill. Could we make observations? Could we collect samples quickly and decentralized in a way that would help policy and response to a future marine disaster? So what do we do? Well, we measure the concentration of these isotopes in seawater because ultimately that impacts how much makes it into the base of the marine food web and to higher trophic levels. And we did that both using traditional oceanographic sampling platforms, big ships out in the Pacific and the Arctic, but we also recruited a network of citizen scientists who would collect the sample every month and send it to the lab for analysis. We measured and looked for levels of contaminants in the marine biota, and then we brought that information to the public, writing op-eds, doing interviews, TV, and posting the data more or less in real time as we generated it. I'll begin with the Open Ocean Sampling Program. So this is using ships to go out to Ocean Station Papa. Here on the right-hand side, you see Vancouver Island and Haida Gwaii, the Aleutian chain here in Alaska. And we've got an icebreaker that leaves every July and heads north into the Arctic that we sample as we head across the North Pacific and up through the Bering. And then the John Tully, Canadian Coast Guard ship, 3 times a year occupies Ocean Station Papa, and we sample on the way out there. And here you see the North Pacific current coming and bifurcating into the Alaska Gyre, bringing contamination towards us and circling around and up towards the Arctic, and in the California current south. It appears that the Americans definitely had dibs on naming the currents off of British Columbia here. So what have we found? So here is a graph that's showing in the upper 400 meters of the water column with Ocean Station Papa P26, 1,500 kilometers offshore on the left-hand side, moving towards the coast in each panel, and moving from June 2013 through August to June 2018. So 5 years worth of data here. And what you can see is that we first started to detect Fukushima-derived contamination relative to the blue background that existed from weapons testing before the disaster. We first started to see Fukushima contamination in the ocean offshore in June of 2013. And you can see the bulk of that contamination in the upper mix layer. So as deep as winter mixing is able to mix it here in this part of the Pacific in the upper 200 meters, arriving and pressing towards the coast through February 2015 with maximum activities of about 10 becquerels per cubic meter. Okay. So the color bar seems to have gone missing off the right-hand side, but the blue is about 1 becquerel per cubic meter or less, and the reds are on the order of 10 becquerels per cubic meter. So that's compared to 100 million becquerels per cubic meter in the port at Fukushima Daiichi in 2011. So we've got horizontal and vertical mixing and decay that diminishes those activities. But we can see that that contaminated water is arriving off the coast and circulating along the coast by February 2010, more or less. So this figure is showing us, again, distance from the coast of Vancouver Island out into the Alaska Gyre. And with time moving forward up the y-axis. And what you can see is that the transport of the contamination was happening at a rate of about 6.6 kilometers per day as the North Pacific Current is making its way across towards British Columbia. And then we have more of a northern component flow as we start seeing the Alaskan Current and interaction with more complicated coastal waters, such that the eastward transport of the plume slows to about 0.8 kilometers per day. And again, you can see these maximum levels in the heart of this contaminated plume that was formed in 2011 off the coast of Japan, about 10 becquerels per cubic meter offshore, and values that are more typical 2 perhaps to 3 becquerels per cubic meter closer to the coast as we move towards Vancouver Island. And we were able to compare this transport with models of physical transport of the plume, of the contaminant plume, with our measurements. So what we're looking at here are dashed lines from a model published by Rossi and others in 2013, which predicts the arrival of the plume off of British Columbia at Ocean Station Papa around 2014, and then peaking in about 2015 or 2016, and then diminishing to levels that are more consistent with the pre-Fukushima background by this year in 2020. And the circles represent our observations at the coastal station P4, the station intermediate distance offshore P16, and in red, Ocean Station Papa, 1,500 kilometers offshore. And you can see that for the most part, the models do a pretty good job of capturing the transport of the contamination. The timing of the arrival is pretty good, but we're seeing that the models were underestimating somewhat, not by very much, but the peak levels that we're seeing offshore on the order of 6, perhaps to 10 becquerels per cubic meter in the subsurface. So we were allowed to sort of ground truth these models by using our observations. And in this blowout panel here, you see cesium-137 from the late 50s at the height of atmospheric weapons testing was around 30 to 50 becquerels per cubic meter, diminishing due to decay and mixing with time. And here are our measurements after the Fukushima disaster showing those levels relative to the weapons testing fallout as we head towards the end of our project. So to put this into perspective, if we go back in the Irish Sea in 2008, mostly from fuel reprocessing, there were levels of cesium-137 on the order of 40, perhaps getting as high as 60 becquerels per cubic meter. Here you see at the height of weapons testing on the order of 100 becquerels per cubic meter. That diminishing with time due to decay and mixing. We see a blip in the North Pacific from the Chernobyl disaster in '86 and falling off towards the disaster at Fukushima in 2011. And the peak levels that we saw off North America were on the order of about 10 becquerels per cubic meter, or similar to the levels that existed back in the 1980s and around the time of the Chernobyl disaster in the Pacific. So These results aren't without precedent. Now, we were also interested in understanding what was happening along the coast, mostly because that's where a lot of the recreational fishing is done and subsistence fishing is done along the coast of British Columbia. Here's Vancouver Island here. This is the Olympic Peninsula down here. Seattle is sitting down here. And here you see the communities where we were able to recruit volunteers to collect the seawater sample every 20 liters of seawater every month and send us that water for analysis in the laboratory for cesium isotopes. So we had about 600 volunteers come forward, and we've had 16 of these communities sampling monthly up until the end of the project in 2020. And the people who came to help came from all walks of life with the common thread of having some passion about ocean health and wanting to be able to do something to understand what this disaster that happened thousands of kilometers away might mean for them and their livelihood. And so we have instructors in colleges in the north in Prince Rupert, a 13-year-old Megan Ives and her mother on Haida Gwaii sampling for us, whole schools and communities in Bella Coola and Powell River taking samples for us going forward in time. It was really fantastic to meet all these people and to learn about them during the project. It's one of the things I enjoyed most about the project. So what have they found? Now, I know this is a busy plot. It's regionally sorted levels of cesium-137 in the seawater collected by our volunteers right at the coast, right at the beach over time. And you can see that areas that are more exposed to the open ocean, like Haida Gwaii, like West Vancouver, the coast of West Vancouver Island, tend to have higher levels and the contamination arriving earlier. But that we see the total amount of Fukushima-derived cesium sort of peaking at about 3, maybe 4 becquerels per cubic meter in 2017 and 2018, and a trend towards lower values and very low values right along the coast, where freshwater inputs from the continent, there tends to be a lot of rain here in British Columbia, and we have the Fraser River coming into the Strait of Juan de Fuca and the Georgia Strait. That's diluting that ocean-borne contamination. So we barely see any trend upward along the coast, for example, here in Victoria or in Vancouver Harbor. So a maximum contamination level of about 3 becquerels per cubic meter relative to that 1 or less than 2 becquerels per cubic meter that existed before the Fukushima disaster began. This is just a very schematic summary plot of all that data. Here's our ocean monitoring data offshore, peaking at around 10 becquerels per cubic meter and diminishing in time offshore as the heart of the contamination moves past that sampling site, 1,500 kilometers offshore. And here's our coastal values coming up towards 2 or 3 and then starting to trend downward beginning in about 2019. And for perspective, here's that 1960s atmospheric weapons testing right off the coast here at about 20 to 30 becquerels per cubic meter. And Health Canada's action level for intervention, where drinking water becomes unsafe for consumption, is 10,000 becquerels per cubic meter. So you can see that these levels in seawater off the coast aren't expected or known to represent a significant health risk to either marine organisms or people who rely on the ocean for recreation or for food. We also did look at marine organisms, and early on in the project we focused on Pacific salmon, and that's because salmon are both culturally and economically important to people in British Columbia and in the north. We went on to look at sharks and whales and oysters, other shellfish, mushrooms as well on land to look for contamination from the disaster as well. But the Pacific salmon are accumulating this contamination both through their gills, like from the seawater directly, and from their food, from the marine food web. So we wanted to know what levels we could expect and whether or not those would represent a health risk. In the back of our minds too, we were hoping that there'd be added value to these measurements insofar as with an evolving contamination field in time and space, perhaps the levels of contamination that we saw in different populations of different Pacific salmon species might tell us about where they were spending their time in the North Pacific. They go away for 4 years, they get big, and then come home, but we still don't know very well where they spend most of their time and what they do. So we hope we might be able to trace where they were going. Now, one of the early results when we had our first batch of fish that were sent off and analyzed and came back, I got a phone call, and I was in Boston at the time in a restaurant, and it was my colleague at Health Canada, Jean-Francois Mercier, and he was like, I have to tell you, I've got terrible news about the first batch of fish. And I thought, oh no, like how high are these fish who we're going to need to talk to somebody about how we control the market and not sell these fish. And he said, we can't detect anything. We can't detect any Fukushima-derived contamination in the fish, which of course is fantastic news. But from our perspective of hoping to get information about where they were going in the North Pacific, it was terrible because there's no signal and nothing could really be done about it. Over the course of the entire project, let me show you what we found. We collected returning salmon from a number of rivers in southern British Columbia and northern British Columbia, as well as fish returning the Porcupine and Yukon rivers in the north. We also collected salmon from the Miramichi River, Atlantic salmon, returning to New Brunswick sort of as a control to look at their levels as well. And this is just a summary of what we found. So beginning in 2014 and heading towards 2018, and comparing the levels of contamination in the fish tissue with what we found after Fukushima with what was measured in fish at the height of weapons testing in the mid-1960s. And what you can see is that we really didn't see much of a trend in terms of average concentrations in the fish. It was always less than a becquerel per per kilo of fish. And in fact, 0.2 to 0.3 was sort of the average concentration that we would detect. Health Canada's action level, where the fish is no longer thought to be safe to eat, is about 1,000 becquerels per kilo. So you can see that after Fukushima, we didn't see levels that were as high as they were during weapons testing, and in fact, they were quite low. And again, consumption of this fish isn't, the health physicists tell us, it doesn't represent a risk either to the fish, to fish including human beings along the coast. So that was the bulk of the scientific results from the project. And in summary, neither the results of our project nor any of the measurements made by the international scientific community suggested that for North Americans, the risk to our marine ecosystem health and to public health was quite minimal. And that Fukushima just wasn't a significant event with respect to environmental or public health here in North America. Now, part of my job and part of my project's job was to communicate this risk to the public as information was coming in. And what I discovered quite quickly, and those of you who have had to communicate about ionizing radiation in the environment, it's challenging. And the reason for that is that we can't see or taste or feel ionizing radiation. And when we talk about nuclear technology, there's this nexus of government, big industry, corporations, and scientists. And that tends to result in a lot of mistrust by the public. So you're already at a disadvantage being a scientist and wanting to communicate about these health risks associated with ionizing radiation. And certainly those of you who are the same age as me or older, we've been conditioned to be quite fearful of nuclear technology and certainly nuclear weapons. Growing up in the 1980s, as the Cold War was starting to come to an end, there were lots of opportunities to learn to fear nuclear weapons, and justifiably so. I put this cartoon in for, well, partly because I love XKCD, but it's mostly for my family and my wife. Are you coming to bed? I can't, it's important. Well, someone is wrong on the internet. So communicating via social media about science is challenging, and you can waste a lot of your time. And so I'm hoping I can help you waste less time if science communication is part of your goal in the future or something that you're active in right now. We as scientists are taught to value empirical information, but when we communicate in public arena about science, we're out of our element. We are faced with situations where emotional appeals, unverified speculation, the current pandemic, climate science, the election, all of this points that sometimes it's not being right or having facts behind you that carry an argument. So how do we operate in this arena? How do we try to make sure that the message that we're trying to send, based on fact, based on scientifically derived information, is received? Well, I've been active. The primary tool of our project was the project website, which you can find at fukushimainform.ca. People go and look at it. All the data is archived there, and I write lots of blogs about both our results, but I also take peer-reviewed scientific literature out from behind publisher paywalls and summarize it in plain language so that people can understand what the international community has been finding about the risk owing to Fukushima contamination in the environment. I spread that information on social media, both with my own Twitter account, the project's Twitter account, and we still maintain a Facebook page for the project as well. And then I give lots and lots of public lectures, probably a couple hundred over the last 6 years or so. Lots of TV interviews and radio interviews, and also interviews with the press. So in response to that, I know there's a silent majority who sees that information and understands it and makes use of it. But beginning in 2014, after I'd done a radio interview with Ken Bissler at an NPR station actually in the Bay Area, I received this email, which said there was going to be a broadcast on YouTube and on an online radio station where we could go and defend ourselves if we wished. Please come. So it was an unsolicited email, and if I were wise, which I'm not, I would have ignored this, but I didn't. And so what started to happen is that in response to this communication, there were lots of people who felt that there was some sort of conspiracy to hide the fact that the Fukushima disaster had destroyed the Pacific and was in fact an extinction level event that was going to destroy the planet. And so I started to be the topic of conversation on Rents Radio, which, if you don't know what it is, I recommend that you don't learn what it is. It's a site that's recognized by the Southern Southern Poverty Law as a hate site. There's lots of terrible things on there, and there were lots of articles and radio shows where my motivation and my the fact that I was an evil human being was discussed quite often. Let's put it that way. And so in response to this, there started to be a lot of emails and telephone calls and nightly YouTube shows where my character, Ken Bissler's character, any scientist who was suggesting that the risks were not catastrophic were being maligned. And you can see some of the titles here: Dark Side of J.T. Cullen, UVic professor. Tora is a fantastic reporter with CBC Radio Canada. And really people calling for violence, and that violence in this situation was justified. And the only way to deal with monsters like me, who, they speculate money from the nuclear industry to try and hide the impact and effectively murdering people by telling them that the risk associated with this contamination in the environment here in North America was small. So this is something that I didn't expect. It was something that I couldn't really understand. And some really creative YouTubers out there. Yeah, lying scum of the earth, government shill murderer is not something that I was hearing a lot up until working on this particular topic and communicating with the public. So these threats escalated to the point where Ken and I were in contact with local authorities and federal authorities in the United States and here in Canada. And the main individual who was inciting a lot of these threats was ultimately charged with criminal harassment, which is a law that's similar to a lot of stalking laws in the United States. And it culminated in September of 2016 with a trial where Ken Bissler traveled up from Woods Hole to testify, and I was in court as well and before a judge to basically to stop these sorts of threats, where I and my family and my colleagues, I'm starting to fear for my safety and not really being able to predict what these individuals who felt this way might do. So the person was found guilty and given 3 years probation. So how did this all happen? Well, the trial was kind of surreal and an odd thing to be involved with, but my wife and I got to show Ken and Wendy around Victoria and had a fantastic dinner, and then sat in court and testified, and ultimately the guilty verdict was handed down. I just want to point out this picture was taken outside of the courtroom here in Victoria, and the defendant in the trial showed up with a Hummer towing this 24-foot Zodiac that they were using to do their research, accusing me of being a shill, taking hundreds of thousands or millions of dollars from industry to lie to the public about my science. And I showed up and left on my bike and left after the trial was over to go back to my office on my 10-year-old Kona Jake. So there's a bit of a disconnect there as well. So now I'll just get briefly to what I think I've learned from this and how I went about learning it. So in the midst of all this going on, leading up to the trial and before, I was trying to sort out, well, why do people believe that these conspiracies exist? Why do they think that I'm being controlled by the Queen to lie to the public about nuclear technology? Like really crazy things that were being discussed. And so I read this book. I found this book called American Conspiracy Theories by Joe and Joe, Joe Uchinsky and Joe Parent, who are at University of Miami. And it turns out that I've read the book, and it started to make more sense to me why people hold conspiracy ideation. Why is this something that's attractive to people? And I knew I was heading to Miami for one of the early Arctic Geotrace's U.S. cruise planning meetings. So I sent them an email and said, hey, this has been happening to me, and sent them some of the text messages that I got or emails and phone messages. Can we get together to talk about this? And they got back to me right away. They were like, this is fantastic hate mail. Like we thought we were getting fantastic hate mail by just writing about conspiracy theories, but this is really choice stuff that you're experiencing. So let's get together. And so I snuck away at lunch one of the days of the meeting in Miami and met them for a burger at this place called Local in Palm Beach, I guess it is, or I can't remember. Anyway, they were pretty funny. They've got a good sense of humor. They told me they were in the back corner of the restaurant looking suspicious, and that's how I found them. Ultimately, this ended up with me being invited to this conspiracy theory conference that happened in 2015. And I was one of only 2 people at this conference of about 50 or so people that weren't actively studying conspiracy theories, but were there to talk about their experiences. So this was being held in the Dwayne Johnson meeting room at University of Miami, The Rock. It was pretty entertaining for me. The only other non-scholar who wasn't studying conspiracy theories, other than myself, was James Tracy, who many of you in Florida might recognize as an individual who was fired from his position as a professor because he thought the Sandy Hook massacre didn't happen. And so when I found that out, I was like, are they having me on? Do they think there's something wrong with me? But anyway, after participating in this meeting, I learned a lot from these scholars about why people choose to believe in conspiracy theories and why it's attractive. And learned basically that sometimes as a scientist, you invalidate yourself as somebody who can be relied on for quality information in certain circles, which was interesting. Ultimately, this led to me writing about my experiences, again, something that I never thought I'd be doing, writing a book chapter about conspiracy theories that was included in this collection of that was published, I guess last year or the year before, that Joe edited, where I talk about my experiences over the last 6 or so years. So what do I think I've learned? And again, I have to be honest and say I'm not quite sure, but I think I've learned the following. If you are going to communicate about your work, and I highly, despite all of my experiences, I highly recommend that you do, because I think it's just fundamentally important that we share what we're doing, why we're doing what we're doing, as well as what we're doing with the public. Ultimately, much of the work that we do is funded by the public. We need to know our end users. Who wants this information? In what form do they need it? Who do you really need to speak to? You want to build relationships with communities. So both knowing your end users and building relationships, we found that we got a lot of traction. I was publishing our results, but sharing our results on fishing blogs and fishing sites. Fishermen, of course, were really interested to know what's going on. And that's when we really started to get a lot of uptake and a lot of traction with communicating with the public. Non-governmental organization partnerships. Those NGOs that I talked about earlier, Surfrider, the David Suzuki Foundation, they are already connected with all of the community that you want to reach. There's no need to reinvent the wheel. They already know who's passionate about ocean health. They already know how to talk to them and how to reach them. I was sitting in my office one day after we announced that we needed volunteers, and I had a couple of emails coming in, and I was building a spreadsheet so I could contact these potential volunteers, when all of a sudden my inbox went nuts. And then I ended up having to write a Python script to process all the emails and populate the spreadsheet. And all the website traffic was coming from David Suzuki. So Suzuki's foundation had put up a call, and that's when we really started to get all these volunteers. They really know what they're doing, and they're professionals. They have a lot of expertise in talking to the public and knowing the public. And last, I would say that citizen science involvement is really key and was fundamental to the success of this project, insofar as people want to help. In the face of some of these environmental problems that we face, the scale of which can be daunting, people can feel helpless. But by making observations or by contributing their own expertise, their local expertise, they have that contribution to give, and they can make your job of trying to understand what's happening in the environment much easier. And you get to meet fantastic people who are really excited about learning about what you're up to, but they also bring to your attention other potential problems or other things to think about. And by having citizens involved directly, it also lends some legitimacy or some transparency to the whole process itself, especially for topics that can be just fundamentally controversial when it comes to public interaction. So I'm going to stop there. I just wanted to point out that if you want to reach me outside of this particular lecture, my email is easy to find at the University of Victoria. I'm easy to find on social media, so I tend to use Twitter quite a bit. My handle is simply my name, which is sometimes easy to remember. And the project website, fukushimainform.ca, there's lots and lots of great information there. I humbly submit from the project that if you are communicating with anybody about ionizing radiation, how it's measured, what levels existed before or after the Fukushima disaster, especially as we come up on the 10-year anniversary, I think it's a really useful resource, and I would point you in that direction. Thanks very much.
Thanks very much, Jay. I've seen some of this a few times. I'm still shocked when I see it, but thanks very much. I think we'll take some questions. Normally we begin with students first, if there are any. Please put your hand up if you have a question. I'll call on you. Kara?
Hi. How's it going? So I actually look at coral reefs, and I think we all know that humans probably are the most detrimental thing to them. And then I also heard about, them dropping or doing practice nuclear testing at Bikini Atoll in the 50s or so. And I was wondering if there was ever any data recorded on any kind of water quality parameters or anything like that that would be of use or they would release. I was just curious.
Yeah, actually, Carol, it's a great question. There's a lot of measurements that have been made, and I would point you to Ken Bissler's group at Woods Hole. So the Center for Marine Environmental Radioactivity, CMER. Ken was just there last year collecting samples both in the lagoon and at the site. There's actually a dome that they buried a lot of radioactive waste from buildings that were demolished and basically encapsulated it in this concrete tomb. And the measurements in the lagoon itself and of the dome and the potential for leaking from the dome are well documented. So you can definitely detect that these tests had been made there. Some enormous yield weapons were detonated there, vaporizing large parts of the reef. The marine communities there have more or less recovered, but there's still some concern. Certainly, terrestrial food webs are still not really safe there, I don't think. But I would point you in the direction of Ken's group. They do a lot of work there.
Cool, thank you.
Mm-hmm.
Okay, thanks. Do you have any more students? Please put your hand up if you want to ask a question. Otherwise, I'll throw it open to anyone to ask questions. See, Leslie.
Hi, Leslie.
Hi, Jay. Good to see you. Thanks very much for a fascinating talk. And also, Tim, I just want to say I really appreciate the background. That made me laugh properly when I when I came in. I had a question that was about the treated water releases that are coming up. And I think one thing that I found quite striking from the talk is in the UK, certainly, we've traditionally seen conspiracy theorists as being quite harmless and something like flat earth and things like that. But I think what you've quite powerfully illustrated, and we've seen it with anti-vaxxers as well, is that actually conspiracy theories can be extremely harmful to people. And with that in mind, I was thinking forward to what they're doing with the treated water on site at Fukushima, which I believe is going to be released from 2022 onwards or whenever. And my question was, one, whether that incident has led to any sort of resurgence in some of the conspiracy theories in Canada around Fukushima, and related to that, whether you or indeed any of the other groups have any plans to try and extend the monitoring to deal with what's coming up.
So before I answer Leslie's question, I should point out that Leslie's probably joining us from Scotland. And he's an expert he works really closely with some of the coastal communities in Japan, especially some of the fisheries cooperatives that are still trying to get back on their feet. And this potential of disposing of the wastewater at the Fukushima site in the coastal environment again is something that, of course, is not welcome news to anybody who depends on the coastal ocean for their livelihood. And so Leslie's the expert on this, and I would urge you to get in contact with him if you've any interest in understanding what the challenges faced there are. So there will be a 10th year anniversary conference where the scientific community gets together and talks about what we think we've learned. There are a number of interviews that I've done over the past couple of weeks addressing this plan to dispose of the radionuclides that are still on site. So there's about a million tons of seawater that are currently being stored at the Fukushima site that were used to cool the reactor and are contaminated and have been, to some extent, there's been an effort to remediate, to remove the radionuclides. Now, to answer your question, in Canada, we're continuing to make the measurements offshore, and we'll continue to do so because they're really useful for sorting out things like mixing and advection. There's scientific grounds outside of contamination to look at it. I don't know. the coastal citizen science component is going to end. The magnitude of the releases, if that were to happen, and there's lots of legal obstacles and other obstacles for ocean disposal of the waste, it's not clear that they would lead to concentrations that would be measurable or detectable here along the coast of North America. Of course, the story is completely different in Japan.
Great, thanks very much.
Sure. Good to see you, Leslie.
Thanks. Brianna?
Yeah, hi. Sorry, don't have my camera on because my internet's been pretty spotty, and having the camera off seems to help. But a really cool talk. So you mentioned the fact that since you couldn't detect the radioisotopes in the fish, you couldn't really use it for any tracking. I was wondering, were there any like stable isotopes that were particularly associated with the Fukushima output? And has anyone looked into whether those being deposited in various quantities would be able to be used for tracking of fish or others?
The fission products that are being generated in significant amounts there aren't stable. I'm not aware of stable isotopes coming directly from the spent fuel that would have utility. There's a fair amount of 14C still in the tanks at the site, and other isotopes, radioactive isotopes like tritium, for example. There were certainly detectable levels that impacted the ocean distribution. There's some esoteric ones that I was interested in at first. An isotope of silver that might have been messing with some of our analysis here, but I don't think that there's a lot of stable material, just because the amount of material, even the amounts of radioactive elements that were released to the environment, we're talking about kilograms of material spread globally. And so I don't think that there's any impact on the stable isotope fields associated with those releases.
Okay, thanks.
Okay. Any more questions? Bob, did you want to? Yeah.
Yes, Jay, really very, very interesting. I wanted to ask if there are any interesting stories to come out of strontium-90 observations.
So strontium-90 was high on our list of concern because anybody with experience thinking about atmospheric weapons testing knows it's rather insidious. Like, it gets into human beings and it stays there for a long time, and it can cause a lot of problems. The nature of the meltdowns and the fact that there was a significant component of the releases that were in solution rather than through combustion, the cesium-137 to strontium ratio was much, much, much higher for Fukushima than it was for Chernobyl. And so the total amount of 90 strontium that was released was relatively small, meaning that where we couldn't detect cesium-137, the marine field for 90 strontium was about 100-fold below that. So because the extraction and detection of strontium-90 is so labor intensive, once we were able to verify that plume signal was very poor in 90 strontium, we invested much less time in looking for it because it was so far below our limit of detection.
Very good, thank you.
Anyone else with questions? I guess if not, I wanted to ask about the Irish Sea, because having spent most of my childhood growing up in North Wales, that seems like a lot of radioactivity. I guess it's below concern, or is there other concerns about fish there?
I'm not an expert on the fish or the health impacts there, but I do know that there was a lot of concern with kelp and harvesting and consumption of kelp, because the kelp, and certainly with shorter-lived radioisotopes like can be an issue. So I think that a lot of isn't there some sort of bread that's made with kelp or with I think that there was some exposure related to consumption of coastal seafood that might have represented a more significant risk to health than what we're seeing here off the West Coast.
Yeah. somewhat disturbing to see on the map.
Yeah, yeah. It's a surprise. It's one of those things that is, it's changed over time, and the releases are lower than they used to be in the past. But there's much of what we understand about Arctic circulation comes from the releases from Sellafield and La Hague making its way, the transit times across and around the Arctic circulation.
So useful in some ways.
Yes. Well, it's just oceanography seems to be full of stories where some environmental disaster provides us insight into ocean circulation, or leaded gasoline, chlorofluorocarbons destroying the ozone layer, but by helping us understand ocean ventilation, all of these potentially silver linings, but perhaps not making up for the environmental damage done in the first place.
Yeah, we talk about that in chemical oceanography, so it's a good example.
Yeah.
Okay, if there's no more questions, normally what we do is turn our mics on and give a round of applause. Thanks very much for coming and talking to us. It's just a shame we can't take you out for dinner and show you nice Florida weather.
It'd be great. It'd be great. Yeah.